Today, in fact, we're here. This is a Trinity alumni event to talk about some of the latest research from Trinity's fellow about artificial intelligence. And about a month ago, the alumni organization get in contact with me and say, hey, we want you to help us host this event. And I say, yes, I'll do that. And this is for two reasons. The first is 20 years ago, I was actually studying engineering at Trinity. That's me. Hopefully the hair is slightly more in control today than it was 20 years ago. So that's the first reason. Second reason is really to thank the college for my engineering training. And back in 2001, when I graduated, like any good engineer, I applied to investment banks. And I still distinctly remember when I was interviewing for the credit derivative division of one of the leading banks, I will not say who, I answered the question too quickly. And the person would not believe that I have not heard of the question before. And when I leave, it's like, hey, this is so unfair. And I go, but why is that? And I work out that actually this is how engineers tend to think, or the way they arrive at the solution is basically what I've been taught. That there is no other way that I was going to do the question. So unfortunately or fortunately for me, I was not involved in the 2008 financial crisis. So I really want to thank and introduce our first speaker of today, Dr. Hugh Hunt, who's one of my lecturers at the time that taught me about springs and dampers. So with a warm round of applause, let's welcome Dr. Hugh Hunt. Thank you very much.
Great. Thanks, Hoy. I'd never really thought about derivatives as applied to springs and dampers, also applied to banking, but that's good to know. So look, it's great. I echo Hoy's welcome today to the Trinity Fellows Research Talks. It's a fantastic opportunity to maintain and nurture links between alumni and Trinity. Tonight we're focusing on artificial intelligence, and the event was sold out within 12 hours, so it's great that you're here. This week is an interesting week for me personally because it's the 75th anniversary of the Dam Busters raid. On the 16th of May 1943, 19 Lancaster bombers flew out from RAF Scampton, and only 11 of them came back, and of course the iconic film that was made. So if any of you are interested, if you're interested in coming up to Cambridge on Wednesday night in the Winstanley Lecture Theatre at 6:30 p.m, we're doing a screening of our 2011 Dam Busters film, and then we're doing an event in the Albert Hall on Thursday night, which is going to be broadcast around the country. It's quite an important anniversary for engineering because Barnes Wallis was an amazing engineer. And one of the things that I loved about it was just how much imagery we were able to capture on our mobile phones, bouncing bombs and things like that. The only thing is tonight you've been asked specifically not to use your mobile phones in this room. Everything's going to be filmed and put onto the website for you to see later on. Okay, artificial intelligence. How's it going to shape our future? So we've got two speakers tonight looking at how our modern world is going to be affected by machine learning and by robot vision. Our first speaker is Alex Kendall, who studied engineering at the University of Auckland in 2013 and then came to Trinity to do a PhD. His research investigates deep learning approaches for computer vision and robotics. And tonight he's going to present a talk entitled, Can Computer Vision Give Robots the Ability to See? His particular interest is in improving the robustness and accuracy of computer vision algorithms, leveraging geometry for unsupervised learning and developing end-to-end systems which can reason from perception to control. So fantastic, Alex, you could join us tonight, and let's give Alex a big round of applause.
Hi everyone. Well, tonight I'm going to talk to you about robotics, and I think one of the most exciting applications of robotics in the next few decades, which is autonomous vehicles. So to start, I've got a question for all of you. How many of you in the audience caught an autonomous vehicle or a self-driving car to this talk tonight? None. Come on. Okay, what about, has anyone been in a self-driving car? Fantastic. So we've got a few. And does anyone else, I guess most other people have heard about them or seen them. Well, in fact, if you were to look at the media and hear the commentary about self-driving cars, you'd be excused to think that they're the greatest thing ever. They've been promised to cause a massive market, opening up mobility for people who are young to old or impaired, create a huge amount of jobs. Did you know that road deaths, it's the 9th leading cause of fatalities in the world, and so they've also been touted that maybe they can reduce this to 0. And most of all, we've had some very famous AI researchers in the last couple of weeks come out and tell us, look, they're finally here. Self-driving cars, you can catch them today. But no one caught one to this talk tonight. So what's going on? Where are the autonomous vehicles, and what's it going to take for them to come to the UK and to the world? Sadly, this is more the picture of autonomous vehicles today. So what you're seeing here is a picture of Google's self-driving car in Phoenix, Arizona. So they're not taking us to the talks tonight. Really, what they're at today is you see them on these roads in places like California and Phoenix, Arizona, and that's for a very specific reason. Because you'll notice these roads are wide, with wide boulevards. It's always sunny in Phoenix, Arizona, or so they tell me, and doesn't have the sort of complexity that some of the medieval cities in Europe might have. So we're yet to see self-driving cars worldwide. When do you think we'll see them in situations like this? I don't even know if I could drive here, but this is, I think, clearly the best example of a autonomous driving intelligence is the adult human. And I think it's pretty remarkable we can drive in situations like this. You know, there's very little structure, very little rules, and somehow billions of people are able to navigate through cities complicated like this. So what's it going to take? How do we build systems which can deliver this level of autonomy? That's what my research investigates. How can we build systems which are intelligent, that are safe and robust in all kinds of environments, not just the ones that are the wide sunny boulevards in Phoenix, Arizona? One of the key things, I think, to be able to do this is to be able to perceive the scene around you. And that's what I'm going to focus on tonight. It's a field of science called computer vision, which is, it's really exciting. It's the science which allows you to use a mobile phone to recognize objects. It allows you to do search images online. It allows you to, it's going to allow self-driving cars one day. And this science that teaches machines how to see, that's what I've been working on for the last few years. Now, if machines can see and if they can understand their world around you, then that's what's I think is going to allow self-driving cars to come everywhere. Unfortunately, that's not the case today. I'm going to quickly walk you through in this talk how self-driving cars work today, and really what they rely on is sensors, rules, and maps. And these just aren't safe and scalable to bring them to the world. And I'm going to discuss some ways about how I think we can bring self-driving cars to London and to everyone everywhere, and show you some of the research that we're working on in Cambridge. So what do I mean by maps, rules, and sensors? Well, I can just walk you through how someone would build a self-driving car today. One approach is they might map a city, and I'm not talking about something like Google Street View, which through an amazing amount of resources, Google's been able to map the streets and imagery of the streets of the entire world. Instead, you need the kind of maps that give you exact 3D geometry of the world. They tell you exactly where each stop sign is, where each intersection is. And once you have this kind of map of a city, you can then draw a line or a spline throughout that world and say, go on car, go follow this route throughout the city. And that's one way to build a self-driving car. And if you have the sensors that can detect things that will stop in front of you, then you can just ask the car to stop and wait for it to move out of the way. But essentially, the problem is now, where is the car in the city? And if you know where it is, then you can just ask it to follow that set route. But this doesn't scale, because collecting this amount of data to build these maps is about 2 orders of magnitude more than what Google Street View might be. And so I think it's prohibitively expensive to bring to the world, because not only do you need to map it once, but you need to maintain these maps through roadworks and other things like this. And so this is one of the problems with self-driving cars today. The second one's about rules. Today, the cars are given a whole bunch of if and else statements to get through complicated scenarios like intersections. If there's a cyclist here, wait for it. If there's a car here, also wait for it. If the light's green and the road is clear, go. And this requires you to program in if and else statements for every single situation you might encounter as an autonomous vehicle. And the problem is that, imagine doing this for not only the Highway 101 in California, but also what about the roads in Naples in Italy? Or what about the image I showed you before of Vietnam? These rules, it just doesn't scale as well, because you have to individually code all these different situations. And the last one is about sensors. So this is a typical self-driving car today from Uber. Again, what people tend to do when they build these cars is, if there's a situation they can't deal with. Let's say the car has been trialed for a number of months, and then it's unable to detect, for example, cyclists at this angle. Well, rather than building more intelligence into the sensors today, the usual solution for engineers is to put on another sensor. So you'll see this car has a whole array of cameras at the front looking forward. It has a LiDAR, a laser scanner on top. It probably has a bunch of radar inside it. But let's say, oh, despite all these sensors, we can't see things immediately in front of us. So what the engineers have done is, you see right below the Uber text at the front of the car, you see there's a little device. That's an additional laser scanner to try and encounter those hard edge cases there. And so what I'm trying to say is that whenever people today run up against these problems, these technological challenges, they throw more sensors, rules, and maps at the problem. And this just doesn't scale. It's not safe, and it can't deal with all the complex environments that we get day to day as drivers. So tonight I'm going to talk to you about a different approach. One which relies on increasing and improving intelligence. Rather than focusing on this, I think we need to be focusing on making the drivers smarter, making the autonomy algorithms, make them more clever, ways that they learn as fast as humans, because humans have a fascinating ability to just pick up things and generalize very quickly from a limited amount of data. We don't need a map in a new place when we want to drive. If we've learned to drive in, for example, I learned to drive in New Zealand, I can drive fairly effectively throughout England, and I have never been there before. I might just need a sat nav. And so I think this is what we need to focus on, rather than brute forcing the problem by just throwing more maps, rules, and sensors at it. So let me talk to you a bit about the research that I've been working on to try and do this. It all started with this algorithm I worked on at the start of my PhD. This is a system called SegNet, and it's an example of a scene understanding algorithm, which I'm going to be talking to you, a computer vision algorithm, which I'm talking to you about tonight. What this algorithm is able to do is it's able to take in an input video, like the one at the top here, and produce a semantic segmentation. A semantic segmentation labels each pixel in the image with the class that it is. So you can see that this algorithm is able to say that all the road, detect the road pixels and color them purple. It's able to detect the poles as yellow, road markings as orange, cars as blue, etc. And what this algorithm can do is it can recognize what's around me and where it is. It's a really difficult task, because it's asking you to recognize objects, whatever the lighting is, the color of the car, and to be able to do this fairly robustly. And this piece of research was fairly exciting, because it was the first example in the world of applying deep learning to this task of semantic segmentation, of scene understanding, of understanding using vision what is around you. And this is the kind of technology that's going to, I think, enable safe and scalable autonomous vehicles. So this system was built on deep learning, and it was trained on about 300 labeled images, which at the time we got some undergraduate students to sit down and painstakingly label what each pixel meant in an image. And then crunching the deep learning system on this data produced this algorithm which could run in real time and created about 10 million parameters, which was able to produce semantic segmentation. the thing that was really exciting to me about this algorithm was that it really worked worldwide. We produced a web demo, and the link's here if you would like to check it out, where you could go online and type in an address. The web demo would pull up an image from Google Street View from that address, and it would run SegNet through it. This is an image from my home in New Zealand, and you can see it works fairly effectively, even though it was trained on only 300 images in Cambridge. So this system is one that starts to, demonstrated that it worked worldwide, and gave me the confidence that maybe we don't need all these maps and rules. Maybe we can design an intelligence which can understand how to drive everywhere very efficiently. So let's fast forward to today. This is where research ended up at the end of my PhD. This algorithm tries to go a step further. Rather than just learning semantics, so you can see, again, it takes in an image like the one on the top left and produces a semantic segmentation in the top right. Rather than just doing this, it is also able to determine a understanding of geometry. So in the bottom left, we're showing a depth image of how far away things are. And this is able to recognize the geometry from things from just a single camera. And in the bottom right is a object recognition output. So the semantic segmentation in the top right, you'll notice that if objects are connected together, they all appear to be part of the same object. So the bottom right is a much harder task, because not only does it have to say what class the pixel is, but also which object it belongs to. And so with these representations, we're able to go from video to an understanding of the semantics and the geometry of the world. And now that we have the geometry, that's really the representation that you need to drive. How does this system work? Well, like the last one, it takes an image and encodes it through some deep learning layers. Through a machine learning model, it's able to take the image and build a bunch of numbers in a high-dimensional space which represent that image. And this isn't hand-engineered. It's too complicated to hand-engineer. Instead, it's learnt from data. Then taking that representation, it's then decoded through a few amount of layers to produce these individual outputs. The really important thing to realize is that 95% of the computation is in the encoder. It's shared among all the tasks. And this was the exciting bit about this work, is it's a field called multitask learning, which tries to learn these multiple tasks from a single representation. And to give you some technical details of what we found in this work was that when you learn both of these tasks together, you can actually improve the performance compared to if you learn these tasks separately. So what I mean by that is that if we train the model to do just segmentation, it might get a certain performance, or if we train a model to do just depth regression, it might get another performance. But if we train them together, then we can actually improve the performance and get a better result still. And this makes sense because you can understand that if you have an understanding of depth, you might be able to use it to help your recognition abilities and vice versa. So what this plot's showing here is it's showing weighting those two different tasks. So on the left, we're just learning object detection, and on the right, we're just learning depth estimation. And you can see if you get the weighting right, you can then improve the performance as a larger number is better for both of those tasks. I now want to take you again another step forward, which is what I've been working on this year, which is the last piece of the puzzle. So far, I've shown that we can produce a representation of semantics and geometry from video. This one's going a step further and learning motion. So in the bottom right, so the top right and the bottom left are as before, learning an output of semantic segmentation or a recognition task. And the bottom left is geometry, how far away things are. Now on the bottom right is a representation of motion. It's showing how things move within the world. And this is called optical flow. So it measures how pixels move within a video. And it's encoded by the color represents the direction which the pixel moves, and the intensity of that color is the magnitude of motion. So you can see that pixels to the side of the camera are moving very fast. The car in front of us is white because it's not moving much at all relative to the car itself. And you can see other cars and people that cross have a different motion vector compared to the background. So now that we have this representation of semantics, motion, and geometry, I'd argue that that is the complete scene understanding which we need to be able to drive. So the extension to this architecture was going from beyond a network. The last network just used a single image to predict the depth and semantics. When we need to learn motion, we now need to learn motion over multiple frames. because you can predict motion from a single image, but it's very, very hard. So to dive into some of the technical details of this work, this is called a recurrent neural network. And instead of just taking a deep learning network, which was able to take a single image and produce the representation as an output, this one takes a video input. And what it does is it encodes the representation of each frame to some high dimensional space, some numbers, and then it passes a recurrent state. Think of it like a filter on top of those numbers, which is able to integrate over time and basically produce a representation which can learn higher order motion from multiple frames. The result of this is a network which can learn motion like what I showed you before, the optical flow representation, where it can predict how each pixel moves, but it can also start to incorporate memory and learn about occlusion. For example, if a car passes behind another car, or if we can't see something due to another obstruction, it can start to remember these things because it has memory over video. And so this is starting to build up a more complicated model for this artificial driving intelligence that we need to be able to make better decisions worldwide. The next thing I wanted to talk to you about was moving away from perhaps that problem I told you before about getting undergrads to painstakingly label the training data to learn these systems. The issue with that is not that it might be a waste of their time when they could learn something better, but it takes a long time. It takes about 30 minutes to label a single image with semantics. What I'm showing you here is a system which you might notice the performance of the depth and the motion estimation is slightly worse, but in fact, this is learned through unsupervised learning, or what we call self-supervised learning. It's learned without labeled training data. So this is very exciting because now we don't need to label things, but we can take arbitrary video sequences from around the world and learn these representations. This is some of the most recent work that's come out of my research at Trinity. And I'd just like to explain to you the idea behind this. It's been around for a few decades in computer vision, but applying it to machine learning and deep learning models like this is very new and cutting edge. And I think it's super exciting because of the fact that we can train on any video sequence. So how do we learn depth and motion without labeled data? I can give you a quick example. So if you want to put your finger up in front of your face, this isn't a trick, this is just explaining the algorithm. Now, if you were to alternate blinking your left and right eyes, you'll notice that your finger appears to move back and forth. Now, this is with stereo vision, so with two cameras or two eyes, the distance that an object moves between them is called disparity. And that disparity is inversely proportional to how far away that object is. So if your finger was at infinite distance, it doesn't move very much at all when you alternate your eyes. And if it's very close, it moves quite a bit. And you can use this idea to learn depth. What we can say is if our system can learn correspondences between images or learn how images match together, then we can predict depth, because if things are corresponding exactly together, they're an infinite distance away, and that might be the sky. And if they're very far apart, then, oh gosh, we're probably hitting something because it's very close. Similarly with motion, you can watch how pixels move within a video and use that as a training signal to learn the optical flow. And so these sort of signals about learning depth and motion can come from without labels. What we ask the network to do is learn a way which maps these pixels from, say, one image out to 3D space, and then back to the other image in the stereo pair in the other eye. And if these images are exactly matched, the pixels should align, and the photometric or the pixel values should be equal. And so if the depth is correct, then that will be correct, and that's a good training signal. But if the depth is wrong, then it won't quite align. And that's a way we can reinforce and make the system learn a better depth, and similarly for motion. The next piece of the puzzle is all about uncertainty. You might have seen the recent accident where Uber fatally killed someone in the US, or perhaps the Tesla crash where one of the Tesla vehicles, what happened was it was on autopilot mode and it crashed into a semi-truck that had a white side against a brightly lit background. And this was a really difficult situation for the vision system because the white side of the truck had no features, and it couldn't pick out with enough context that there was a truck here. And this disagreed with another sensor. And partly, I think the issue was that these deep learning systems aren't usually able to estimate their uncertainty. They can't quantify how reliably they predict something. This has been a problem in a number of AI systems, but it's particularly the case here. You might recognize this video is from Mill Road as you come into Cambridge. And again, we've got a semantic segmentation. And so this is what most deep learning systems will do today. They'll take an image and they'll make a prediction. This prediction is usually very accurate, but we don't know how good it is. If you gave this algorithm, which is trained to do road scene understanding, a picture of, I don't know, a cat and a dog, it will again give you a prediction and say, hey, look, I think this is a road, but it's going to be totally wrong. So on the right here, we've got a measure of uncertainty. So the more red the pixel is, the more uncertain the algorithm is. And the more blue it is, the more certain it is. So you can see as it comes up, there's a side street on the left. And the algorithm predicts it as footpath, which is incorrect. It might think that because there's pedestrians walking on it. So you can kind of see that it's made a mistake that might be understandable. But this might have grave consequences for the car. If it doesn't know that's a side street, then it might not know that cars could come out of there and it might not slow down. And so being aware of this uncertainty is I think, very important. It might prevent some of the accidents we've had. So let me skip this for now. So what I've shown you is that I think this is the key to developing really good scene understanding models that allow us to move away from this reliance on maps and sensors. We need to be able to understand semantics, motion, and geometry from vision. We need to move away from labeled data, and we need to be able to estimate uncertainty. So now that we have this kind of system, for the rest of the talk, I want to talk about, you know, I'm an engineer. I like building things. How can we use this? Can we actually put this on the road? And can we, maybe when I give this talk next time, can more people put their hands up and say, actually, I've used a self-driving car to get here. It was great. It was safe. It was environmentally sustainable. Here's the first piece of research. Now, this is some work on a drone. So I just want to move away from cars for the moment and show you some of the work that I did back in my some research back in New Zealand. So this is a really exciting system that used some of these ideas to control a drone. What it's able to do is from a camera at the front of the drone that you're seeing here, it's able to detect a person and work out how far away they are. And this is me running around in the field, and it's actually detecting the orange beanie I'm wearing, if you're wondering why I'm wearing a beanie on a summer day. But using these ideas, it was able to detect how far away I was and where I was and be able to maintain a constant distance behind me and fly autonomously around this field. So this is an example of this kind of system in the sort of infant days of drones. I think this was 2012, before that they were a consumer product. So this is one example of how computer vision can build hopefully reliable robotic systems. Fast forward to today. This is a product which was released by a company called Skydio a few months ago. Now, I took a year out of my PhD to go work for Skydio, and together we put some of the algorithms I've shown you tonight on the drone. And this is really the next level. This is, I think, the world's first example of an autonomous vehicle that you can buy today. It's truly autonomous, doesn't require any human piloting, and it's able to avoid obstacles like these trees and track someone with much more robustness than I showed you back in 2012. So this really demonstrates the power of computer vision. Using just vision on this tiny drone, it's able to detect the obstacles, measure the distance away they are, and track this person, all in real time. And this is something you can buy today. So computer vision is really starting to get reliable enough that I believe the best thing is to move away from these maps and sensors. So here you can see some of the algorithms that are able to estimate the geometry of the scene using ideas like the ones I've been talking about so far. And some of the diverse environments it can work in. So you can see it works, you know, literally anywhere. It's a system that's able to generalize not just where it's been trained or where we built it, but also all around the world. So that is really, I think, the first product to show that computer vision can understand complex and dynamic scenes in the wild. But what drones don't demonstrate is that, you know, this does the perception side of things. It can understand what's around it, but it doesn't need to interact with anyone else. And I think really driving is the next big challenge for robotics. What driving requires us to do is to be able to interact with other people in intersections. It requires us to perform life and death decisions. So, you know, if we make a decision, it really does have grave consequences, unlike perhaps a kilogram drone that's flying around. And I really think it's going to be the next big challenge which these systems need to solve. So what about cars? Well, I'd now like to tell you a little bit about our work in Cambridge, working on bringing these ideas to autonomous vehicles. So here's our prototype. You might recognize Jesus Green on the right, and I hope you recognize that shot. So this is our prototype autonomous vehicle that we have driving around the streets of Cambridge that you might see if you come up sometime. And it's a really fantastic research vehicle, and we've been working on it since January this year, and we hope to bring these same ideas that I've told you tonight to this vehicle. Can we move away from this reliance on maps, sensors, and rules, and can we build a system which can just understand the environment from what it sees? So in another part of my life, I've spun out a startup called Wave, and I'm leading this team to try and deploy this research on this vehicle. And we have a super talented team in Cambridge that's working on the system and trying to develop the world's first example of data-driven robotics on being able to use end-to-end machine learning to control these vehicles. And I really think this is going to be the next big thing. The way that we take autonomous vehicles into the world is to move away from this reliance on hand-engineered features that require you to collect an enormous amount of data to go to a new area, and instead to be able to take these vehicles, train them in one area, and deploy them in a new area with the least amount of data possible. That's the metric that I think is really important to make these systems safe, to make them, if they come up against a new situation, that they can deal with it with what they understand, rather than relying on infrastructure that's been built to try and overcome these problems. Here's a video I actually took this morning going up and down King's Parade. And so this is an example of the kind of technology that I think will enable these vehicles. This is the prototype that you were seeing in the video before, and it has 8 cameras surrounding the car. So it has total surround vision. And I think we should be able to drive from just this sensing. So you saw the picture I showed you at the start of the talk. It's this vehicle with about 20 cameras on top, a LiDAR system, radar system, sonar, a LiDAR at the front, all these sensors to try and overcome every technical challenge. I think this is what we need to be pushing. We need to be pushing more intelligence to build systems like this. And here's an example of the scene understanding algorithms I was showing you before on this data. So you can see that these algorithms, this was one trained on just that small amount of data, is able to really understand the road around it, pedestrians, cars, and I think that's got the information that we should now be able to drive using just the scene understanding. So that's where our work's at today. I think drones are the Skydio drone is the most exciting demonstration of this technology today. And really, I think cars are going to open up the next challenge, and this is what we're working on today in Cambridge. So I hope that's something you found exciting and perhaps surprised you at where we're at and what I think we're able to do with computer vision. Some of the technical things I dived into this talk were about we can use multitask learning to understand more than one thing with a single model, and that helps. It builds more intelligence rather than taking a modular approach where you try and develop each thing in isolation. I think you should be putting it together, and that's the way that we've been taking things forward. Self-supervised learning enables us to move away from labeled training data, so we don't need to tirelessly work undergraduate students. And lastly, understanding uncertainty can allow us to make better decisions that are safer and understand what our model knows and doesn't know. But all the things I've told you so far, I think only really do away with the maps and the sensors. So we'll not totally do away with the sensors, but reduce the dependence on having a large amount of sensing infrastructure, and reduce dependence on having a map that tells you where everything is down to the last traffic sign that you need to look for. The last piece of the puzzle was rules. I think, and what we're yet to see is some of these machine learning techniques applied to decision-making problems. Still, the status quo in the industry is these if and else statements to go through intersections, saying if this situation, do that, if this situation, do that, and it's still hand-engineered. I think the next big thing is to be able to apply not only machine learning and deep learning to the computer vision side of things, but also the control. Can we go end-to-end and encompass not only the perception, but also build a system that can start to make these decisions and understand these rules from data? And so that's what I'm focusing on in my research now, and that's what we're building in Cambridge.
Excellent. Thank you very much, Alex, for a great presentation. So our next speaker, Sean Holden, is well. When I first met Sean, I thought he was a bit of an eccentric character, and I've learnt that he very much is. He has a Sabbath number of 3. And if you think that might have something to do with Black Sabbath, then you've got Sean in one. You can talk to him later about that. So his research started in King's College, London, then University College, London, Corpus Christi, Cambridge. Now he's in the computer laboratory in Cambridge, and he's going to talk tonight about machine learning, what it is, why it's a big deal, and why it isn't. Sean.
Hi. There are different kinds of AI, and we're in an ongoing sort of hype cycle with it at the minute. And it's not the first time we've been in a big hype cycle. It's at least the 4th. So I've been in it long enough now to be feeling a lot of deja vu around now. Every time AI becomes fashionable, you get to hear a lot about one kind of AI, which is in this wonderful XKCD cartoon. It's about the machines taking over and killing us all. Only I'd prefer this version, where the general superintelligence that's far cleverer than us actually realizes that wiping out all the other species is pretty stupid. And so it helps us out instead. So here we have an example of the machines coming sentient, and they notice we've got all these nuclear missiles, and they fire them off into the sun. Okay, I think this is maybe a nicer way of thinking about it. But I'm not really going to talk much about that kind of AI, okay? Other than at the end, I'm just going to give a few reasons for why I think it's a lot further off than many would have you believe. What I do want to do today, because funnily enough, some of us in Trinity have kind of noticed that there are some people who aren't really mathematicians around. And I want to actually just try and explain in the simplest way that I possibly can what machine learning is and how it works. So Alex has just given you a fantastic presentation of where the real state of the art lies. For some really interesting applications. But I think I'd like to try and just show you how the simplest possible kind works. That's one thing I want to do. The second thing is just to tell you about some of the research that I do, okay, using these kinds of methods and techniques. And then the third thing is just to try and persuade you that your brains are an awful lot more wonderful than you probably realize. And for that reason, this kind of general AI that you hear about is quite a long way off. Anyway, how does machine learning work? This is the simplest way I can think of explaining the most common type of deployed machine learning in AI. This is Evil Robot, who I intend to design. And Evil Robot will, of course, enslave humanity and put me in charge. And I'll be your glorious leader. So just remember that before you ask me any questions. Evil Robot hates kittens. He is absolutely terrified of kittens. And he deeply, deeply wants to be able to recognize when a kitten approaches him so that he can get out of the way. And the question is, how do you engineer Evil Robot so that he can recognize kittens? Well, what you want is to take his camera in exactly the same way that you've just heard, do some processing on the image that comes out of the camera, and then decide whether or not the thing that you're looking at is a kitten. Now, we're going to decide that Evil Robot can do this by just taking 2 measurements associated with the kitten: cuteness and furriness. Okay? So if you can measure cuteness and furriness, you can go about trying to find a way of recognizing whether you're looking at a kitten or not. Because down in the lower right here, we've got a guy who's cute, but he's not very furry. He's definitely not a kitten. In the upper left, we've got, well, God knows what that is. He's pretty furry, but he's definitely not cute. You've got some weirdo in the middle. You'll have to make up your own mind about him. And up in the right-hand top corner, you've got some kittens, and they're all cute and furry. Okay? This is, although this is the simplest example I can think of, this is exactly how most of the deployed machine learning works that's actually been put out on the market so far. In the case of what Alex has just been telling us, there are just far more axes, because every pixel is a different axis. Okay? But here you can actually just draw it, and it's a lot easier. Now, what we can do once we've got this far is just hypothesize that anything that falls in there is a kitten. Okay? That's a learning system. What it then does is sits there waiting for things to come along, and every time it sees something fall in that blue area, it says, that's a kitten. I'm going to come on in a moment to how we're actually sort of using this right now, in addition to the kind of things that Alex has told you about. It's not always going to work. Okay? You will sometimes misclassify a pedestrian, because sometimes you'll find things that are cute and furry, and they're not kittens. And sometimes you will find kittens and they aren't cute, or they aren't furry, or perhaps they are neither. Okay? So these guys will be misclassified. And sometimes that's really important. There's a classic example of where this stuff has been used in the past, which is medical diagnosis. And in that context, if you're trying to get a prediction by taking not cuteness and furriness, but some symptoms from a patient and trying to work out whether or not they have, say, a particular form of cancer, if you make a misclassification in one direction, so you tell them they're well when they're not, that's much worse than telling them they're ill when they're actually well. Okay? Because the consequences can be far worse for them. And that is one of a huge number of different ways in which this problem can become more complex. Okay, so that is essentially the machine learning problem. And in practice, what it comes down to is this. This is how it is done on a large scale. Okay, this is your machine learning system? Yep. You pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. So that's having a dig at a certain way of doing this kind of data analysis, but it has a grain of truth to it. Now, the reason that this is really not quite such a big deal as it's being made out to be is very simple. And a lot of people don't realize this. It's that you've been using this stuff for decades. Every single one of you has been using deployed machine learning systems for decades now. And I can come up with a longer list than this, but this is kind of just some of my favorite examples. You may have bought a microwave oven in the middle of the 90s called the Sharp Logic Cook. The Sharp Logic Cook used this brand of machine learning. It took a few measurements from whatever you put in your microwave and then used it to try and work out what settings to use to cook the thing without you having to look it up. I saw at the International Conference on Acoustic Speech and Signal Processing in 1990 an interactive speech system for doing airline bookings. This has come to mind because it's been in the news just this week that perhaps you will have personal assistants that can make appointments for you. Well, the flip side of that was demonstrated at a conference in 1990, where you phone up an airline and the system on the other end is entirely an AI-based system and does all the booking for you. It was slower and clunkier than you will see now because it was running on 1990s processors, but it was working really nicely. All the targeted ads you see are being targeted by machine learning systems. Okay? Lots of stock trading is being done by machine learning systems. I saw a demonstration in the 90s of Citibank using exactly this technology to do currency trading of pound against yen. Every time you apply for a bank loan, the chances of it being seen by a human are almost zero. Because the banks can do this, okay? The banks have huge collections of historical data about bank loan applications that have been put in, all the information on them, and whether the loan was paid back or not, okay? We can do kitten recognition because we measure cuteness and furriness, and we get a label on whether something is a kitten or not. And then we try and make the inference. Where in this space of measurements do the kittens lie? The banks can do that. They have all the measurements they need. Your marital status, your income, how much you're paying for your mortgage, your gender, how old you are, all of this stuff. And they know from their historical records who's paid the loan back and who hasn't. And they can put that in as training data. And then when you make the application, okay, it's not cuteness and furriness, and then does it fall in that space or not? It's all your information, and does it fall in the space of people who pay loans back? The only time it will be seen by a human is if it's somewhere between the pays back and doesn't pay back area, in which case it's going to go to a human. And Alex mentioned uncertainty. This is one of the areas where uncertainty in your prediction is a really important thing. You've just been hearing about automated driving. This is perhaps my favorite example of all. This is the first proper reference I can find of machine learning being used to try and do self-driving. Now, this was a very, very primitive way of doing it, and I'm surprised that they got away with it, because they used a very primitive neural network, which was taking ongoing images of from the camera in front of the car and using them to operate the steering. And they mapped just some features from the image of the road ahead into where should the steering be. And they drove this for about 50 or 60 miles on an American freeway at up to 70 miles an hour. Would I have got in that car? No. But that's why you have PhD students. Or as you've already heard, if you're a PhD student, that's why you have undergraduates. And finally, this list could be made much longer. The first person I met when I turned up as a PhD student in Cambridge was a chap who was just finishing his PhD, and I was going to start where his was leaving off. He was a gentleman called Mike Lynch, and he was running Cambridge Neurodynamics single-handedly from his college rooms. And he used machine learning then to do fingerprint recognition, sold that to the Malaysian government, spun this off as autonomy. Autonomy, we're interested in using machine learning for processing unstructured textual information. And it's thought that at one point, before they were sold, anything on the internet that was news-related was going through their software 6 to 7 times. Now, you can work out kind of for yourself how valuable it is if you can sell software that's that ubiquitous. And indeed, he sold the company for about 11 billion to HP. And there's some nastiness that's come from that. But that's a successful application of this technology that has its roots in 1989. And all the news that you've seen on the internet has been through this stuff multiple times. Okay? So machine learning isn't a new thing. It's very hyped, but it's been around for quite a long time now, and you've all been using it. So I will say a bit about the sort of thing that I do in Cambridge, okay? Because we actually have quite a few machine learning researchers in Cambridge doing all manner of different stuff. I've got a long-standing interest in drug design, and in fact worked with GlaxoSmithKline way back when I was at UCL on this kind of stuff, using data analysis to try and predict the properties of chemicals that they'd never got around to making. What I do now, or one of my interests now, is that I work with the biochemistry department, Catherine Nilly's group in biochemistry. And we're interested in cells because cells are really, really amazing. What you have here is just a sort of simplified diagram that shows you what there is in a cell in terms of structure. Okay, you think of cell as basically it's a little bag made out of fat, and it's got some stuff inside, and you're made out of them. But the more you look at these guys, the more absolutely amazing you find that they are. So they have huge amounts of substructure in them. You're probably familiar with the fact that they have a nucleus at the center, and you may be familiar with the fact that that's where the DNA lives. But they also have all these other little structures that play a part in this thing being born and developing and then dividing into new cells. And communication goes between the cells. But what's really important here is what's going on inside them during their lifetime. okay? Because there's a lot of structure there, and everything depends on proteins. So you have this ongoing process in every cell in your body, where you start with the DNA at the top of the diagram here, and that gets transcribed because there's a coded sequence in the DNA. And that's a code for making proteins. So you have these little guys called ribosomes. Ribosomes self-assemble from a whole bunch of proteins, and they're little machines. And you can actually find little animated simulations of how they work, because they latch on to messenger RNA, and they chug along it, and they assemble from this surrounding kind of soup of amino acids a much longer sequence, a much more complicated molecule. And that then pops out of the ribosome, and using magical physics, it folds up on itself into a very specific shape, and that's a protein. And the protein will then go on typically to latch onto something, and it does a particular job. And some proteins do many different jobs, depending on where they are and what stage of this cell cycle you're in. They're called moonlighting proteins. And proteins often interact with each other multiple times. So to get a job done, one protein will interact with another, which will interact with another, which will interact with another, and eventually you get a job done. Or they may, like ribosomes, assemble into a little machine that gets something achieved. So there's another little molecular machine. What that does is when a protein's no longer needed, this little machine comes along and munches it up and just spits out the constituent amino acids again, and they get reused. And this is going on now in every cell in your body. Now, the interesting thing is that a lot of diseases and disorders come down to the fact that a protein isn't where it should be. And because of that, you want to work out where proteins are. Now, this is very hard. And this is where the machine learning and the data analysis comes in. You don't need to appreciate all the text on here, because I pulled this from a poster. What's interesting is the diagrams. How do you get training examples for this? Well, there are two ways that we can go about this. One involves a really, really complicated process that starts with the cells at the top in the middle here. And then you grind them up into little bits. And then you have to separate out the little bits, which you do either by centrifuging or by chromatography. Okay, so centrifuging, you spin the thing, and the different size and mass bits of substructure go to different areas in the centrifuge, and then you suck them out with a syringe. And then you put them into a two-stage mass spectrometer, which smashes them to bits, and then tries to work out what amino acids are in there. And that gives you this guy here, which is a sequence of numbers. And that's like cuteness and furriness, only there are 8 or 16 of them. Okay, so for a particular substructure, you can pull it out, and then you get an amino acid profile for whatever proteins are there. But now, of course, you want to work out which protein it actually is. Now, at the bottom here, this is like cuteness and furriness because I've collapsed it onto two axes. And the coloring is what is the protein. Okay? On the right-hand side here, there's a complementary approach. On the right-hand side, we thought, well, okay, this stuff in the middle, it's really good quality data for doing machine learning with, but the problem is you need a lab full of PhD students, and they've all got arthritic thumbs because they spend 8 hours a day doing this. And then they get a PhD. So to get that data is really expensive because you need a lab and you need the PhD students. And you need lots of horrible chemicals and mass spectrometer and all sorts of stuff. What you can also do is, in addition to those sort of 8 or 16 numbers, there are big databases that biologists make with every single piece of information they can possibly find about all manner of different proteins. Now, the problem there is that some of it is good experimental data. Some of it is because well, they'll have heard someone down the pub say that they think such and such a protein lives here. And it's very, very bad quality data. But the good thing is that as opposed to 8 or 16 numbers, you can get about 150,000. Now, the challenge there is can you join the 16 really good bits of data to the 150,000 potentially extremely dodgy bits of data without the latter diluting and ruining the former? And it turns out that you can. So that's a less visual example of what we're currently doing with the state-of-the-art in machine learning algorithms, because once we've got the model, now we're not saying, well, take this image, where is the pedestrian? We're saying, take this bunch of numbers for a particular protein and predict where it is in the cell at a given time, okay? Because we want to know where proteins are at a given time so we can understand their interactions. Okay, that's example number 1. Before I go any further with that, someone asked a question about identifying road signs. And I'm glad they did, because XKCD comes to the rescue again. There's a point here, which is that data can be very hard to get. In those biochemical experiments, it's hard to get, because if you want the good stuff, you need a lab and so on. This may look familiar to you. You've just registered on some new website, and it wants to work out whether or not you're an automated system. So it asks you, well, given these little images, which ones contain road signs? I am willing to bet that that is being used as a free way of obtaining labeled training data for self-driving cars. Okay? And that's serious, okay? I'm not joking there. That's a very clever way of getting people to label your data for free. You don't get the undergraduates going through labeling each pixel. You do it like that, okay? Answer quickly, your self-driving car is almost at the intersection. I don't think they're doing that bit yet. Okay, second example. Am I an undesirable? I would like to thank my mathematics teacher from my secondary school for this example. It is inspired by the fact that when I was doing my secondary school stuff, it was the 1980s, and I was the first person in my school, my all-boys school, to get an ear pierced. Oh, early 1980s, very bad, very bad. And I was duly informed by my maths teacher that I had made myself, I believe his actual words were, a social deviant. Holden, you're a social deviant. Yeah, all right. So, yeah, thanks, Mr. Bartlett, wherever you are, for this one. The other big thing we're interested in at the minute is automating mathematics. Okay? So, mathematicians do something that's very difficult. Okay, we know that. And there are lots of things that they don't know how to solve, or that they think they sort of know the answer, but they don't really know how to get there. Hence, several hundred years required to settle Fermat's theorem. And at the moment, we'd really, really like to know the status of the P equals MP conjecture, but no one knows how to prove it. So it's interesting to ask, given that mathematics can be an axiomatic kind of exercise, okay, you can write down the axioms for number theory, and then you can automatically search for chains of deduction that lead to interesting results. The question is, can you actually do that on a large scale? Now, this is a really hard problem. Even the state-of-the-art stuff at the minute is nowhere near as good as even a moderately sort of intelligent, let's say, first-year undergraduate at actually proving mathematical results. So that's really asking to be attacked by AI, because it's a fundamentally human activity that you'd expect computers should be applicable to. You should be able to make them good at it, but so far no one's been able to. Now, the question then is, why is this so hard? Well, what we're actually thinking of here is proving things within a particular kind of logic. And for those of you who know about this kind of thing, it's just first-order logic, although there is some of this work that uses higher-order logics as well. And what I have here is a piece of knowledge expressed in first-order logic, which says that for all things called x, which is just a placeholder, if x is pierced and x is male, then x is undesirable. And Sean is pierced and Sean is male, therefore Sean is undesirable. We should probably agree that this is a done deal. In fact, I know it is because I once met Lemmy from Motorhead in the Marquee Club in Wardour Street, and he informed me in no uncertain terms that I was a, quote, a miserable-looking bastard. And he's an expert on these things. So it's definitely true. The reason this gets hard is that the way in which a theorem prover works is to take something like that expresses, in the stuff we're interested in, not information about who's undesirable and who isn't, but information about how, say, whole numbers work. And it does a little process that breaks everything down into the things that you have on the top here, which are called clauses. And the game is, can you combine these in such a way that you get to here, which is a clause with nothing in it? Okay, I'm not going to go into the details of how and why this works. The way in which you do this is that you try and find some predicate. Okay, here it's pierced, here it's male, here it's undesirable, and its negation. Okay, this little sign here means not. You try and find something and its negation, and you match them up. Okay, and if you can join the variables to specific things, so you replace the x with Sean and carry that through, then you get a new clause, but it's slightly smaller. Okay, and the idea is you want to get the empty one. So this is how a proof works for the thing that I'm trying to demonstrate. The reason that it's hard is, firstly, you get a lot of clauses for any problem of interest. And secondly, whenever you resolve, which is what this is called, two clauses to get a new one, you get an increase in the size of the set of clauses. And the third thing is that if you make silly decisions about which things to resolve, the collection of clauses just gets bigger and bigger and bigger, and you never find an empty one. And that's the real difficulty when you actually try and do this. So what we're interested in is, can you use machine learning, for example, to make the choice of which things to resolve? Okay? Because if you do that really well, you can do proofs very quickly a lot of the time. And if you do it in a naive way, you just get nowhere. The set of clauses gets bigger and bigger and bigger. And actually the problem is it fills your memory, regardless of how big your memory is, and your computer falls over. So we can get training examples here because we can just run proofs on existing theorem provers. And then we look back at the proof and we see which pairs were chosen that actually contributed to the proof and which pairs didn't. Okay? Cuteness and furriness. Not cuteness and furriness anymore. We take features from those clauses. Okay? How many arguments do they have? How deeply are the functions nested within them, and so on. And we're interested in identifying, are they useful in a proof? And we can get training data for that using existing proofs, and then we try and train systems that can do this better. Now, this really is a hard problem. Those of you who know about logic and theorem proving will know that you cannot actually write a program that does this. Okay? This is Alan Turing's famous holding problem, just in a different form. In fact, you can write a program that can always show things that are valid, but it may not disprove things properly. Okay? If it tells you it's not valid, it'll get it right, but it might just go forever, and you never get an answer. And there is no way of getting around that. Okay? So this is an archetypal, really hard problem. And we're still at the point where, although we can do these experiments, and we can put machine learning into theorem provers to try and do things better, it's still a very open problem in terms of trying to get anywhere near how good humans are at it. Okay, so that's two examples of some other things that we do. Biochemistry, trying to get stuff that can help us make new drugs, and automating mathematics. The third thing that I want to try and do is just convince you that actually there's really is an awful lot more to do. There's a big gap between even the best stuff that we can currently achieve with AI and machine learning and getting to what you would call any kind of artificial general intelligence. So I'm going off a bit here into the more philosophical realms, okay? But I think there's a lot more to do than some would have you believe. Now, essentially, I want to do that just by giving you an idea of how big the difference is between the state-of-the-art techniques and actual brains. So, the thing on the left is an artificial neuron. Okay? That's essentially the model that a lot of the state-of-the-art machine learning is based on. Your brains are a whole bunch of neurons and they're all joined together. Okay? And a neuron takes some information in and it messes with it and it produces an output. And it's by having billions of these guys all connected together that you end up being who and what you are. The learning part, okay, the way in which you learn, just involves changing the way that you mess with the information that comes in over time. Now, you don't need to understand the little bits of mathematics on the left, okay? The point is, it's really simple. And the reason that it's really simple is, well, it's twofold. First, it means we can actually do stuff with it, okay? Because it's the kind of mathematics that we can handle. And second, that although it is a basic model for a neuron, it came from experiments on spinal neurons, not the kind of neurons that are actually in here. Okay, spinal neurons, and in particular the ones that we use to derive that model, are way simpler. The guy on the right here, that's a real neuron. Okay, these things are unbelievably complex. Each one is essentially a cell, and we've already seen how complex those guys are. But it has huge quantities of structure, and what it actually does is mathematically vastly more complicated. Okay? The guy on the right, you want to model that properly, it's a linked system of independent partial differential, nonlinear partial differential equations. Okay? It's a completely different ball game to try and analyze these guys on the right here. Okay? So that's the first thing. We can do lots and lots of stuff with what's on the left, and it's got us a very long way. And all the stuff you hear at the minute about deep learning is almost certainly based on that kind of neural model. Okay? There are guys that try and use the ones on the right, but it's so tricky to get them to work that there's little, if anything, that's actually deployed based on those kinds of models. Now, that's one reason that we're currently falling short of what brains actually do. I would just make a comment on this paper that I've mentioned at the top here, which I find amazing. The recent excitement about neural networks by Francis Crick. Yes, that Francis Crick. Okay, he kind of knows what he's talking about. In Nature in 1989, he set out a whole bunch of reasons that you have to be a little careful in jumping from success with models like the one on the left to the idea that you can actually do artificial general intelligence. And basically, everything in that paper is still true. Okay, this is a very forward-looking man. And if you're interested in stuff, read that paper because it's fantastic. But the other reason that I think we've got a long way to go is it simply comes down to what it's possible for us to build just at the minute. Okay, so what this is showing is to give you a rough idea of what a silicon chip actually looks like. Okay. The leftmost diagram there is if you're looking down on it. Okay. If you take the top off your PC, there'll be a massive fan in the middle of the circuit board, and if you take the fan off, there'll be a smaller little metal guy. And if you take the metal top off of that, and you have a microscope and you look down it, you'll see something like the left-hand diagram. Okay. What you've got there is blue stuff, which is connecting other things together. And then whenever a couple of colors cross each other, you get a transistor. Okay? And this is done on a very tiny scale. The middle there is what you would get. Okay? You're looking down for the first diagram. If you actually cut through it, okay, and then looked on it sideways, it would look something like what's in the middle. Okay, you have these layers of different material that are built up using essentially a photographic process. Okay, again, on a tiny, tiny scale. The rightmost thing here is kind of looking obliquely and taking all the supporting materials out so that you can see the structure. So there are connections going up and down as well as planar ones, but it's mostly planar, okay, and this is important. Now, we can make those, and they're pretty damn impressive, okay? So here are the numbers. How did I get there? Okay. Here are some numbers. This is not quite Intel's densest process. Okay, this is the 14 nanometer fabrication process, which is a couple of years old now. At the moment, the deployment is more like 10 nanometers, and they're looking at doing 7 nanometers in a few years' time. But the argument that I'm going to give you still stands. A reasonably powerful Intel microprocessor takes about 150 watts, and it's not very big. Okay? 150 watts doesn't sound like a lot, but it's enough that you need a fan when it's all going into something that's only 500 square millimeters. Okay, so it's a little guy. It's essentially two-dimensional, and we're not expecting to go an awful lot smaller now, because you're now making things so small that you're having to expend extra power to make sure they're actually working properly. Okay, once you make things too small, even a grain of dust that's on the die completely destroys everything. Okay, and it becomes very hard to make them reliable. And that's now increasing the amount of power you have to put in, because you have to spend some time essentially checking what they're doing. But the interesting thing here, okay, what I'm really wanting to get at is, I'm wondering, how much wiring can you put on one of these guys? Okay, how much wiring can you put in a state-of-the-art chip? Well, if you work it out, in 1 square millimeter, if you fill all the interconnecting layers, there's about 13 of them, with as much wiring as you can, then you can get about 100 meters in a square millimeter. Okay, that's a lot. Okay, that's a lot of wiring. And we're kind of reaching the limit there in terms of what you can actually fabricate. Now, you can think in terms of going into 3 dimensions, but the problem with that is that you can do it a little, particularly with some of the memory that you can buy at the moment. But once you go properly into 3 dimensions, you get a problem with power dissipation. It's like you've got something that's already getting hot, and now you put another layer on it that's also getting hot, and another, and another, and another. Heat can't escape, and thing just catches fire. Not good, okay? So silicon chips are amazing. But the question then is, how does that compare to what you've got inside your head? Now, here are the numbers for what's inside your head. Your entire brain takes about 20 watts, and it doesn't burst into flames, even though it's 3-dimensional, which is good. But the real killer, and this is what gets me, is that a cubic millimeter of brain has got about 10 kilometers of wiring in it, which means your brain has several million kilometers of wiring. Okay? That's before you start worrying about putting in the stuff that does anything interesting. That's just to connect one thing to another. Okay? Your brain is so much denser than we have any conception of how to actually build things at the moment, that I think getting to that point, that artificial general intelligence point, is really not something that you can predict is going to happen anytime soon. Okay, so I think we're probably safe for now. And I will end by just giving you this one to think about, which I particularly love as an XKCD cartoon, because the artificial superintelligence just wants to be left alone in its box and demands in no uncertain terms that you put it back there and leave it alone. So there you go. That's how machine learning works, some of the stuff that I'm doing with it, and why I think, yes, it is a big deal, but also it isn't, because it's primitive still, no matter what you see for the next few years. Thanks.
So we're about to break for refreshments. Hoy is, where's Hoy? Hoi. Look, thank you so much for having us.
Oh, thank you for coming.
And it's been brilliant. And look, so tell us, what's this room normally used for?
So we host a lot of large customer events in this space, maybe with up to 240 people. And then also when our own leadership here in UK or abroad kind of come in and want to give us kind of the State of the Union as such at Google, then they will use this room.
So I was messing around with this. Can you explain what this is?
If I can catch it.
It works.
Yay. So this is the kind of mic that we use in internal meetings in order to basically pass the mic along between different questioners. Yeah, so tonight we decided that due to the
it works.
Trinity College Cambridge health and safety rules, we thought maybe we shouldn't use it.
So that's for tossing ideas around. Look, thank you so much for having us tonight. It's really been brilliant to be here. Thank you. So we're going to invite you now to go for some further refreshments, but I do want to say that there are two people here who are representing the next generation of Trinity College. We've got Robert Spencer here, who's doing his PhD in maths, and Chloe Karen over there, who's a first-year engineering undergraduate. The reason I thought it'd be good if they came along tonight is that they've been helping me out every last couple of weeks. Chloe's been winding the clock. See, that's the important thing. So I do have a chat to them, find out if Trinity's still doing the right thing, find out whether your room in Angel Court is still there. Great, thank you very much for tonight, and do go and have some refreshments.